When we compare electron microscopes to traditional light microscopes, the very first and perhaps most crucial difference comes down to the illumination we are using, light versus electrons. Think about the waves. The wavelength of visible light is actually about 1,000 times higher than the wavelength of an electron. This fundamental difference is what allows electron microscopes to achieve vastly higher magnifications and resolutions. They can see much finer details because their measuring stick, the wavelength, is so much smaller. But it's not just about size. Light waves are tricky to manipulate when you want to focus them really tightly beyond what glass lenses can do. Electrons, however, carry a charge, which is a game changer. Because they are charged, we can use electromagnetic fields to act as lenses to focus and direct the electron beam. This is something we simply cannot do with light. And finally, that charged nature also gives us incredible control, just like the old cathode ray tube televisions. Remember those, where an electron beam was scanned across the screen to create an image? We can precisely scan an electron beam back and forth across our sample. This scanning capability is what allows techniques like scanning electron microscopy, giving us detailed surface topography that light microscopes just can't provide. This image helps us to visualize the fundamental differences between light and electron microscopy. At the top, you see the core reason for the electron microscope's power, the wavelengths. Notice how the light wave is long and spread out, which limits how much detail we can see. In contrast, the electron wave is incredibly short and tight, allowing us to resolve much finer features. In the middle, we illustrate how these different waves are focused. Light uses traditional glass lenses that refract and bend light. Electrons, being charged particles, are manipulated by electromagnetic lenses, giving us much finer control over the beam. And the bottom, you see why electron microscopes, especially SEMs, are so versatile. Just like an old CRT television, we can scan the electron beam across a sample, building up an image point by point, which allows for detailed surface analysis. This image vividly demonstrates the practical difference in resolution and detail between light and electron microscopy. On the left, we have a typical view from a light microscope. You can see a permisium and an insect leg, but notice the inherent blurriness and lack of fine surface detail. This is due to the larger wavelengths of light, as we discussed. Now look at the right. This is a scanning electron microscope image of a nanostructure. The incredible depth of field, sharp detail, and intricate surface texture are immediately apparent. This level of detail is only possible because we're using electrons, which have those much smaller wavelengths and can be precisely scanned across the sample. It's truly a leap into the microscopic world. Now, to really appreciate where electron microscopes came from, it's helpful to look at their journey and compare it to the much older story of the optical microscope. I've laid out a simplified timeline on this slide, highlighting 6 key stages in the development of these powerful tools. This isn't just about dates, it's about the conceptual leaps and technological breakthroughs that defined each era. Let's start with stage 1, the ideal geometrical idea. This is the theoretical blueprint, the idea of a perfect microscope with infinite magnification and no flaws. For the optical microscope, this idea emerged as early as the late 16th century with people like Zacharias Jansen. But for electron microscopes, This vision, based on using electrons instead of light, only truly began to crystallize in the late 1920s with groundbreaking theoretical work by people like Louis de Broglie and later Ernst Ruska. The SEM's ideal came a bit later as it built on the principles of electron interaction. Moving to stage 2, early design improvements. For optical microscopes, this meant centuries of work by pioneers like Louis van Hooke, and later advancements in achromatic lenses. For the TEM, these were the crucial early 1930s, just a few years after the initial idea when Ruska and Nall built the very first prototypes demonstrating that electrons could be focused to form an image. The SEM also saw its early designs take shape around the same time, though its path to practical application was a bit slower. Basic understanding stage 3 refers to grasping the fundamental physics behind the microscope's operation. What limits its performance, how the lenses work, and how the signal is generated. For optical microscopes, this understanding matured over centuries. For electron microscopes, it involved unraveling complex electron-matter interactions and precisely controlling electron beams and vacuum systems. Then comes stage 4, commercial availability. This is a critical turning point because it makes the technology accessible to a wider research community. Optical microscopes were commercially available quite early, certainly by the 17th century. For the TEM, it was the late 1930s to early 1940s when companies like Siemens and RCA started producing the first commercial instruments. The SEM also, its basic ideas were explored earlier, took longer to become a robust commercial product, really taking off in the late 1950s and 1960s. This was a huge step, bringing these powerful tools out of specialized labs into broader scientific use. Further design improvements is stage 5 and is where we see continuous innovation. For optical microscopes, this involves phase contrast, fluorescence, and confocal microscopy. For TEMs, it's about aberration correction, cryo-EM, and in situ capabilities. For SEMs, we've seen environmental SEMs, field emission guns for better resolution, and advanced detectors. This stage is ongoing, with each generation of microscopes becoming more powerful and versatile. And finally, stage 6, better technique of use. This isn't just about the instruments, it's about the users. As instruments become more sophisticated, so do the methods for preparing samples, operating the microscopes, and interpreting the data. This stage is crucial for unlocking the full potential of any microscope, ensuring we get meaningful and accurate information from our samples. As you can see from the dates in the table, the electron microscope technologies developed much more rapidly in their earlier stages compared to the centuries of refinement for the optical microscope, really highlighting the accelerated pace of scientific and technological progress in the 20th century. Now, earlier in our discussion, I showed you a conceptual timeline where the scanning electron microscope was represented by a simplified icon. But the reality, the actual instrument, is far more complex and impressive. As you can see from this picture, a scanning electron microscope actually looks like this. It's a highly sophisticated piece of engineering, not just a simple drawing. It's so much more intricate than the little emoji of a microscope you can find on your phone. Speaking of which, it does make you wonder, doesn't it? Given how pervasive and critical SEMs are, In science and industry, when do you think we'll finally get an official SEM emoji to represent these incredible machines? As for when the emoji of an SEM comes out live, well, unfortunately, there isn't one yet. We have a general microscope emoji, but not a specific SEM. Perhaps someone in this audience will be inspired to submit a proposal to the Unicode Consortium. And we have a similar story for the transmission electron microscope. As you can see here, this is what a real TEM looks like, a towering, complex instrument far from any simple icon. And no, we still can't find an emoji for this one either. This makes me wonder, would you from now on still use the common optical microscope emoji or a simple generic microscope JPG to represent all electron microscopes, or will these powerful, intricate machines now demand a more accurate image in your mind? It really highlights the difference, doesn't it? Would it bother your mind from now on when you go to show what you're working on, say on your social media profile, that even if you're using a highly sophisticated transmission or a scanning electron microscope, you can only find a generic optical microscope picture to paste? It highlights that disconnect between the complexity of our work and the simple icons available, doesn't it? Earlier, we looked at different stages in the development of these microscopes, how they evolved from basic ideas to complex machines, and how our understanding and techniques of use also matured. But there is almost an unlisted seventh stage we are grappling with today, especially in the age of digital communication and social media. Let me ask you, would it bother your mind from now on when you go to show what you're working on, say on your social media profile, that even if you're using a highly sophisticated transmission or a scanning electron microscope, you can only find a generic optical microscope picture to paste? It highlights this funny disconnect, doesn't it? Our tools have evolved dramatically, but how we represent them, especially in casual, quick communication, often hasn't caught up. It's a small but interesting point about how technology perception sometimes lags behind its reality. I would like to remind you that understanding this evolution helps you appreciate the current capabilities and limitations. Now that we've discussed the fundamental differences between light and electrons, and seen some real-world examples of their capabilities, let's dive into how these microscopes are actually built. On this slide, you'll see a comparative diagram illustrating the basic layouts of an optical microscope and an electron microscope. This visual helps explain why they perform so differently. On the left side, we have a typical optical microscope. You can see its familiar design. At the bottom, you have your light source shining up towards the sample. The light then passes through the sample, illuminating it. Above the sample, you have the objective lens, which gathers the light that has interacted with your specimen. And finally, the eyepiece at the very top is where your eye receives that magnified light to form an image. Essentially, it's a relatively simple upright path of light traveling through lenses and then into your eyes. Now let's shift our focus to the right side, which shows the basic layout of an electron microscope. You'll immediately notice some striking differences, and most of them relate to the fact that we are using electrons instead of light. First, the electron microscope is often depicted as a tall vertical column. That's because it needs to maintain a very high vacuum inside. Electrons scatter easily in air, so we need to remove as much of it as possible. Instead of a light source at the bottom, we have an electron gun at the very top. This is where electrons are generated and accelerated down the column. Below the electron gun, you see the electromagnetic lenses. Unlike glass lenses, these are coils that create magnetic fields to focus and steer the electron beam. Crucially, the sample in an electron microscope is typically inserted mid-column, often in a special chamber, and the electron beam passes through or scans over it. And finally, at the bottom, instead of an eyepiece, we have detectors or a viewing screen that convert the electron signal into an image we can see on a monitor. So the key takeaway here is the inversion of the light path. Electrons usually travel down a vacuum column, and the reliance on the electromagnetic fields to control the beam. These fundamental design choices are what enable electron microscopes to achieve their incredible resolution and provide detailed information that light microscopes simply cannot.